Reason why I can't let the videos go past 15 minutes, I upload them to YouTube and then from YouTube to Folio. That's just the way I found that worked for me. But uploading to Folio, uploading to YouTube, you can only do 15 minutes. So we were trying to figure out the surface area here. So the surface area of a can was the top plus the bottom plus what we're calling the side. And then I made us a little can here. And so we can see that the top and bottom are just circles. And then when we unrolled the can, the side is just a rectangle. So we had area of a circle, area of a circle, area of a rectangle. There's one of our bottoms there. The area of the circle, just pi r squared. Then the area of the rectangle, well, there's the height of my can. So one of the dimensions, length times width, length times height, is the height. But then I needed this length right here. So let's go for some color. Let's draw a red line here and fold that back up to see what that red line is. So let's make it back into a circle. And what that red line is, and we can see it all the way around there. And I'll go around again slowly. There's my red line. And we trace it all the way around. And now let's unfold it. And what that red line here is just the circumference. And so the area of my rectangle here was the height times circumference. And so pi r squared plus pi r squared plus h times 2 pi r. And we'll just call this area for surface area. And so surface area is 2 pi r squared, because we had some like terms there, plus 2 pi r h. But that's in two variables. I need it in one variable. We need one variable, and so we use the constraint, which was, and you can't see it anymore, but I'll bring it back down, was h equals 1,000 over pi r squared. So we had a equals 2 pi r squared plus 2 pi r h. Becomes 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Simplify. The pi's are going to cancel. The r with the r squared is going to cancel. And we have 2 pi r squared plus 2,000 over r. Or because I'm about to do some calculus, it's going to be easier to say r to the negative 1. And so there is my equation for r on. So now my interval of possible values. Like I said on the previous one, all these things are going to be physical situations. Most of them are going to be lengths and whatnot. Sometimes you'll have, depending on the problem, maybe a number of trees. But negative numbers are just not going to make sense in the applications you see in Calculus 1. So it's always going to start at 0. And then whether you should include 0 or not, the way every textbook goes with is whether 0 is defined in the function or not. If we look right there, if we let r be 0, this becomes undefined. And so it has to be an open interval here. So for open interval, open at 0, and then for this other guy. So the first variable is always your first number is always your primary variable. It's always going to be 0 because that's the way things work in Calculus 1, not in the real world. It's going to be 0, and then you just have to make the decision whether you should include 0 or not. Generally, what we do mathematically, you look at the function, will 0 work in the function? Well, then include it. If 0 won't work in the function, like this one, then don't include it. your second variable, and your second value comes from your second variable, and we need to keep h positive. So h was 1,000 over pi r squared. So if we look at that and we think about it a minute, 1,000, positive, pi, positive, r squared, positive. This is always positive. No matter the value of r. R can be anything, as long as it's positive. Can be any, I'm not going to put anything, can be any positive value. And so that makes my upper limit infinity. That there is no upper limit here as far as maintaining the positive status of h. As long, regardless, even r could be negative. Mathematically, r being negative wouldn't matter. But we'd already decided that r was going to be positive because r is a distance. And so we could have any positive value, so that takes us up to infinity. And so there's my function and my interval. After that, all the steps are going to be basically the same. So that was step 4. Step 5, derivative. So a is a prime. There's my derivative right, there's my original function there. Remember, pi is just a coefficient. So that's going to be 4 pi r minus 2,000 r to the negative 2. Or that's 4 pi r minus 2,000 over r squared. Critical number. Now note there is a does not exist case here. The derivative doesn't exist at 0, but we've already thrown out 0. And that's the way it's going to happen on all the does not exist cases, again, at this level. The does not exist cases here just are not going to be applicable at this level. Mathematically, it could be a different story, but at this level, you're not going to have to worry about the does not exist case. So set my derivative equal to 0. Solve that equation. Clear the fractions. So I'm going to multiply everybody by r squared, excuse me. It's going to cancel there. And so I'm going to have 4 pi r cubed minus 2,000 equals 0. 4 pi r cubed equals 2,000. R cubed equals 2,000 over 4 pi, which is 500 over pi. R equals the cube root of 500 over pi. I do not need a plus or minus for odd roots when I take the odd root of both sides. It's even roots of both sides that I need a plus or minus. And so there's where we think the answer is. But again, that's a critical number. It could lead to a max, a min, or nothing. And so we must verify the status. Must verify. And in this case, they said we wanted to minimize the amount of material. We must verify the minimum status on 0 to infinity. Okay. So step 6, verify my status. This is an open interval. Your best bet, use the second derivative test. So first derivative, let's just do a little recall here. We had a, the original function was 2 pi r squared plus 2,000 r to the negative 1. The first derivative was 4 pi r minus 2,000 over r squared was my first, or let's go with r to the negative 2. That'll be easier to work with. And so my second derivative is going to be 4 pi plus 2,000, no, not 2,000. It's going to be 4 pi plus 4,000 r to the negative 3. So second derivative test said, find your critical number. We did that. Find your second derivative. We've got that. Then plug your critical number into your second derivative. So my critical number was 500, cube root of 500 over pi. Now that in no way, shape, or form is simplified, but I do not care if you simplify that. Please, God, don't. I don't want to check it all. So plug that critical number in there. And I just drop that negative exponent down there. Now, you could do stuff with this, but notice everything there is positive. This equals a positive value. That's all I care about in the second derivative test, whether it's positive or negative. And then remember, if you're just thinking about just positive, negative, and whatnot, second derivative test seems to work backwards. And so that tells me that r equal the cube root of 500 over pi will minimize. And so there I did just verify that I have a minimum, but now be sure you answer the question. The question wasn't just what is r. So step 7, answer the question, and way back when it says, how should we choose the height and radius? How should we choose the height and radius? Well, we already know that the radius is the cube root of 500 over pi. And then recall that we knew that h was equal to 1,000 over pi r squared. And so this is going to be 1,000 over pi times the cube root of 500 over pi quantity squared. And frankly, if I gave this to you on a test or whatnot, I'd be so tickled pink that you got this far and you remembered to verify its minimum status. Wouldn't care at all if you simplified this. So we are not going to go down the road to simplifying. Sometimes in MyLab Math, they let you change things to decimals, and in my math lab, in MyLab Math, they let you go with a decimal. Go with a decimal. Type in your calculator, see what decimal it is. For me, don't give me a decimal, but you certainly do not need to simplify something like that. Just stop. Yes, we could simplify it, but that's well beyond what we want to do. We want to focus on solving the problems globally. And that's the end of this lecture, or this video, not the end of the lecture. We still have more problems to do.